Dear students, welcome to this next lecture of MSc Final Mathematics Paper 5, that is Theory of Generalized Functions. As we all know that we were studying Weierstrass definition of gamma function. Now, today's lecture I begin with the result gamma z, gamma 1 minus z equals pi divided by sine pi z. If you recall, you have already seen this result in your BSc Part 1 Calculus course, and the result similar to this was gamma n, gamma 1 minus n equals pi divided by sine n pi. But there was a condition over n for this result to hold, and that condition was that the number n, which is a real number, it should lie between 0 and 1. Similarly, here for this result, with complex number z or complex argument z to hold, the condition is real part of z must lie between 0 and 1. You can easily track this condition, as I have already told you that as we have seen in the definition of gamma function for real argument, that gamma n is defined for n greater than 0, and in the same way I proved that gamma z to be defined, we must have real part of z should be greater than 0. So in the same way you can understand this condition also. So in order to prove this, we use beta function, and we have seen that beta mn, where m and n both are positive numbers, so real numbers. This for real numbers we have seen that beta mn is gamma m gamma n divided by gamma m plus n. So if we, in the same way as we have generalized gamma function to the complex domain, we can do it with beta function also. So beta z1 z2 will be now defined as gamma z1 gamma z2 divided by gamma z1 plus z2, where there will be certain condition, and that condition is very obvious. Wherever we have gamma functions, the real part of this z1, real part of the z2, and real part of the z1 plus z2 should be, I should say, must be greater than 0. We know that if real part of z1 is greater than 0 and a real part of z2 is also greater than 0, then if we just add z1 and z2, the corresponding complex number that we get, z1 plus z2, is also having a positive real part. Okay, so here what I do is I just find beta function of z comma 1 minus z. So this will be equal to gamma z gamma 1 minus z divided by gamma 1, and that gamma 1 is 1, as we have already seen with the help of Weierstrass definition or Euler's product also. So here, as we can see that there are gamma functions of z and 1 minus z. So similar to these conditions, we have now real part of z greater than 0 and real part of 1 minus z also greater than 0. And if real part of 1 minus z is greater than 0, it means that the real part of z is less than 1. So we have the condition real part of z lies between 0 and 1. Okay. Now, if we just use the definition of beta function here, we can write gamma z gamma 1 minus z as, using the definition of beta function, we have integration from limits within limits 0 to 1, and it will be t to the power t to the this z minus 1, 1 minus t to the this minus 1. So 1 minus z minus 1 will give you just minus z. Okay. Okay, so this is it, and if we just simplify it a little bit, we get 0 to 1 t divided by 1 minus t to the z, and what remains is dt divided by d. You can easily simplify this and you get this. Now we can see that there is a term t divided by 1 minus t, and if we just substitute this t divided by 1 minus t with y and further simplify this, then we can easily see that gamma 1 minus z is equal to the integral from limits this 0, yes, this will, okay, and 1, and you just find the value of y corresponding to this. So you will get limit 0 to infinity, and this will become y to the z minus 1 divided by 1 plus y dy. Okay, so far what we have done is that we have proved that gamma 1 minus z is equal to this integral. This integral involves a complex number z, okay, 0 to infinity, y to the z minus 1 divided by, this whole is in a bracket, 1 plus y dy. Okay, z is a complex number here. So what we are going to do now, we are going to solve that integral with the help of complex integration or contour integration, we can say. So what we do now is, let us consider the contour integration, and what I am going to consider is this contour integration. What was that integral? That was y to the z minus 1 divided by 1 plus y dy. Okay, so y is a real number here, and that real number y lies between 0 to infinity. It means that y is a positive real number. So whenever we are trying to convert it into a contour integral, the integrand also changes, and we just replace this y with a complex number now. Okay, so now in place of y I am going to have something like alpha to the z minus 1, and in the denominator we had 1 plus y. So now I'm going to write 1 plus alpha in the denominator, d alpha. Okay, so here what is c here? So c is simple closed contour, and that contour I'm going to show in a figure. What points you need to keep out of this the region inside C. Okay, so that point must be any possible branch point of this. Okay, and we know that there is a branch point of this, and that branch point is at alpha equals 0. So how is that a branch point? So you all know that if alpha is a complex number, and if alpha is a complex number, so if you are using a function like suppose f alpha to the 1 by 2 or alpha to the 1 by 4, okay, so or any complex power, or you can say alpha to the 1 by 4 plus 2i, okay, so in such cases we certainly have branch points, and where is that branch point? We have branch point as at alpha equals 0. Okay, so you have already seen this in your previous year's complex analysis course very well. So here alpha equals 0 is a branch point, and this fractional power, or you can say 1 by 2, 1 by 4 is also possible there, because real part of z lies between 0 and 1. So obviously you're going to have z something like say 1 by 2 plus 2y. Okay, so if you just find the real part of z, and that real part of z is 1 by 2 here. Okay, so if you just put this 1 by 2 here, what you're going to have, this you are going to get alpha to the minus half, right? So alpha to the half or alpha to the minus half, in all these cases alpha equals 0 is a branch point. So whenever we are trying to solve some integral with the help of contour integration, we must make sure that the region inside the contour C must not contain any branch point, and on the boundary of C we must not have any singularity of this integrand. Okay, so here what I'm going to do now, I have to exclude alpha equals 0, and at the same time I have to make sure that where this denominator is 0, this denominator is 0 at alpha equals minus 1. Okay, if you put alpha equals minus 1, this denominator is going to be 0. So I have to make sure at the same time that alpha equals minus 1 does not lie on the boundary of C. Okay, so now let it be O, the complex number z equals 0, and let us have a circle. Let us form a circle around it. Okay, and do not close it, right? Suppose the radius of this circle is capital R. Now what you do now is have something like a branch cut, and then form another small circle. Okay, now suppose this small circle has radius say small r, right? So this bigger circle has radius capital R, and this small circle has radius small r, right? Now let me name some points here. So suppose that this point is A, then take some intermediate point. Suppose this is B, this is C. Suppose this point is D, right? Now let us name it as E. Take some point here, F, G, H, right? So now give it a direction, this direction, A, B, then C, D, then from D move towards E, D, E. Then if you want to continue the orientation, right? So in a continuous manner, A, B, C, D, E, and then not towards H directly, but you have to go around like this. So E, F, G, H, okay, and then from H towards A, right? So from H towards A. Now this simple closed contour can be named as A, B, C, D, E, F, G, H, A. Okay. The bigger circle has anti-clockwise orientation, and the smaller circle, okay, this small circle has clockwise orientation. This is for this, just for this time being. Okay. Now, so this contour integral can be named as A, B, C. How many parts does it have? Okay, let me define the different curves, simple curves forming this complete simple closed contour. So the first is this bigger circle. Okay, so how many parts does this C has? The first part is this bigger circle, A, B, C, D, you can call it. This is circle of radius R. Okay, what is the next thing? The next thing is A, B, C, D, then D, E. Okay, so next thing is D, E. What is DE? DE is a line segment. DE is a line segment. Then we have EFGH. And what is this EFGH? This is another circle, and this circle is of radius. What radius? Small r. Yes. Then finally we have HA, and this HA is again a line segment. Okay, so there are 4 curves involved in this simple closed contour C. So now let me find what is the value of alpha, because we need to put the value of alpha here, and the value of alpha will be according to the curve where over which it is moving. Okay, so this alpha moves from A to D, that is on this bigger circle. So I have to find the equation of this bigger circle, this line segment, this is smaller circle, and again this line segment. So if I begin, so I should begin from this bigger circle, and we know that if we have a circle of radius capital R and centered at z is equal to 0 or O, then the value of theta will vary from 0, theta will start from 0 here, and from 0 it will increase up to theta equals 2 pi, right? Actually these I think that you all know this, you all have studied in your previous year's complex analysis course. Whenever we have some cuts like this, A and D are shown to be 2 different points, but actually they are not 2 different points. So here A and D almost coincide, and the value of theta will be, this is one complete circle. Okay, don't think like that there is some angle difference. No, there is no angle difference. So theta starts from 0 and ends at D with theta equals 2 pi. Okay, so the values of theta range from 0 to 2 pi, and the value of alpha, or the equation of the circle, will be capital R e to the I theta. Okay, so this is it. Next we have this line segment DE. What is the difference between these 2 points DE? This is a line, and we know that D, E and O, these 3 points are in the same line. Okay, so the argument of D and argument of E will be same, and the argument of D, or you can say that the value of theta, at D is 2 pi. So the value of theta at E will also be 2 pi. Okay, so theta is constant from D to E. Actually theta is constant, right? And if we just assume that the distance of a variable point, suppose that this variable point is P. Okay, suppose that the distance OP is Y, right? Suppose that the distance OP is Y. So Y varies from, this is Y equals capital R, right? Because the radius of this bigger circle is capital R and the radius of this smaller circle is small r. So Y varies from capital R to small r, right? So we have alpha equals Y. In the previous case, R was constant, but theta was variable. Now we have, in place of R, we have Y, and that Y is variable, and theta is constant. And what is theta? 2 pi. So 2 pi I we have, and Y ranges from capital R. sorry, it is capital R to small r. So y ranges from capital R to small r. In the previous case, theta ranges from 0 to 2 pi. Okay, so now we move forward to the third case. This is a circle of radius r. This is a circle of radius r. Okay, and it starts from E. It starts from E, and at E we have theta equals 2 pi, and this circle is traced clockwise. Since the smaller circle is traced clockwise, so theta this time starts decreasing, right? And theta, the value of theta at E is 2 pi and starts decreasing after one complete revolution about O. The value of theta at H, what will be the value of theta at H? It will be 0, right? So for this small circle, we can write alpha equals, what is the radius of this small circle? This is small r. So the modulus at all the points of this circle is same. Modulus represents distance from origin, so that is small r. It is constant, e to the I theta, but this time theta varies from, not from 0 to 2 pi, it is 2 pi to 0, right? It is 2 pi to 0, because if you are going to write it theta varies from 0 to 2 pi, it means that you are tracing this smaller circle anti-clockwise, but this smaller circle has to be traced clockwise. So theta varies from 2 pi to 0, right? Now let us come to this final fourth part of this simple closed contour, and that is again a line segment, right? So again, if you take some point P or Q, suppose the distance is y, right? Now at H theta is 0, at A theta is 0, so theta actually doesn't vary at all. So theta is a constant now, and what you can write, just pause this video and think. Now let me tell you the answer. Alpha will be y e to the power 0 I, because theta is 0 and theta is constant here, but y will vary, and y will vary from this point to this point. It means that from small r to capital R. So I hope this is clear to you all. Now if you just again think about this this contour integration, right? So this contour integration, for this particular integrand, we have two types of singularities. One is branch point at alpha equals 0, and the other one is a simple pole where this denominator vanishes, and this denominator vanishes at alpha equals -1. Okay, here let me give you a hint. Okay, let me give you a hint here, that you take small r very small, as it is small r not because it is small r so you are taking it very small, so it's a bad joke. Not because of small r and capital R you are taking small r very small and capital R very large, not because of this reason, but the main reason behind this is, if you take small r to be very small but not equal to 0, it is not 0, okay, and capital R tending towards infinity, so the advantage you have is that, think about this line segment DE or think about this line segment HA, right? So this line, for this line segment, D tends to infinity and E tends to 0. So the and this is real line also. Okay, this is real axis. It is very easy to see. This is real axis, theta equals 0, and this axis is imaginary axis, right? So all these points D, E, H, A, all these points lie on the real line, and E tends to 0, O, E tends to O. So the limit of y will be from, or so sorry, limit of alpha will be from 0 to infinity, and on this real line alpha is actually y, right? So if alpha is actually y, so what will be the limit? The limit will be y from 0 to infinity. So the advantage you have is that in place of alpha, you will be able to have something like y here, and dy something like this here, and the limit you are going to have is from 0 to infinity. And what integral you are looking to solve? You are looking to solve the same integral, y to the z minus 1, 1 plus y dy from 0 to infinity. Okay, so this is the first advantage of taking this small r very small and capital R very large. Small r tends to 0, but small r is not equal to 0. Why? Because we have to get rid of this O. We do not want this O inside the region because this is a branch point, and also since r is too small and capital R is too large, so very obviously where will be this pole, simple pole? So this simple pole means at this alpha equals minus 1. So alpha equals minus 1 will be something like at this position. This will be minus 1, right? This is 0, this is something like this, here will be 1, this here will be minus 1. And minus 1 will lie inside this region. Why? Because the inner circle is very small and outer circle is very large, so it contains everything, just about everything except origin, right? So let me proceed further. Now let us move to the next slide. So in the previous slide, if we apply that famous Cauchy residue theorem, then we can write that integral I will be equal to sum of residues, sorry, it has to be multiplied by 2 pi I multiplied by sum of residues at poles of fz, or that was, I think, function of alpha, of f alpha. So let me erase this. This was f alpha of f alpha inside C. Okay, so we just consider those poles which lie inside C, and there is a simple pole, only single pole of this function f alpha, and that pole is alpha equals minus 1. So, and since this is a simple pole, so we can very easily find residue at it. And how we do this? We take limit alpha tend to minus 1, alpha plus 1, f alpha. I think you all know this. So now 2 pi I and limit alpha tends to minus 1, alpha plus 1. And what is alpha? What is f alpha? F alpha is alpha to the z minus 1, alpha to the z minus 1 divided by 1 plus alpha. So this 1 plus alpha gets cancelled out, and we get 2 pi I, and on the other side we get minus 1 to the power to the z minus 1. We know that e to the power pi I is minus 1, right? This is a very famous result based on Euler's theorem. So we can replace this minus 1 with e to the pi I, and we can write it as 2 pi I e to the pi I z minus 1. So this is the value of this integral I. Now this integral I, we had seen that this integral I can be partitioned into four parts. The first one is the larger circle. Let me write it larger circle, or you can also write it as what was the larger circle? It was ABCD. So you can just write ABCD. The second part was DE. It was a line segment. What was the third part? The third part was EFGH, and the fourth final part was HA, right? And this will be equal to this. So now for this larger circle, we had obtained the value of alpha. And what was alpha? What was the integral? Integral was actually, I think it was C alpha to the z minus 1 divided by 1 plus alpha d alpha. Now what I'm going to do now is that I'm going to put the value of alpha according to these different four curves. So for this larger circle, we had seen that the value of alpha was capital R e to the I theta, and the limit of theta was from 0 to 2 pi, right? So here we can, what we can place here, in place of alpha we write R e to the I theta, and there is z minus 1. So okay, R e to the I theta whole to the z minus 1 divided by 1 plus R e to the I theta, right? And now if alpha is R e to the I theta, so d alpha is very easily you can find R I e to the I theta d theta. So this is the value of this first integral. Now let us think about the second integral, dE, right? So what was dE? dE was, dE, the equation of dE is alpha equals y e to the 2 pi I, and y varies from capital R to small r. Okay, so y, it will become integral y e to the 2 pi I, and there is whole power z minus 1, right, divided by 1 plus y e to the 2 pi I. And what will be d alpha? So d alpha will be simply, if you just, what is the value of alpha? The value of alpha is y e to the 2 pi I. This whole is constant. So we can write e to the 2 pi I dy, right? So this is it. So this was the value of first integral. This is your second integral. Now I will write this third and then fourth. Here let me tell you one very important thing and very common mistake that the students make. Okay, so the common mistake that the students make most often is that they put the value of e to the 2 pi I as 1. Yes, it is true. There is nothing wrong with it. E to the 2 pi I is, yes, it is 1. But you cannot put it, you can put it here, you can put it here, but you cannot put it here. Why? Because this is the beauty of branch points. You take one complete circle, you started from, suppose you started from theta equals 0, and at the end, you are returning at the same point with theta equals 2 pi, right? But the value, so the value of e to the 2 pi I is 1 and e to the 0 I is also 1. But if you are going to have some whole power of it like z minus 1, then in that case you cannot put the value of e to the power 2 pi I as 1, because depending upon this whole power the resulting value may be different, because suppose you take z to the half. Suppose you take z to the half, right? So this is a very simple and very famous example. If you start from something like argument z is theta equals 0, right? So you can write r e to the, what will be r e to the I 0. You started from this point, and after one complete circle the value of z becomes r e to the 2 pi I, right? And now if you take z to the power half, so this becomes square root of r, right? And e to the power 0 I upon 2, and that is equal to e to the power 0 I, which is 1. But if you put z equals r e to the 2 pi I in this under root z, square root z, you will get square root of r and e to the power 2 pi by 2. Yes, e to the power 2 pi I by 2 you will get, and that will be equal to e to the power pi I only, and e to the power pi I is minus 1, right? So suppose you start from z equals r e to the power 0 I. You start from z equals r e to the power 0 I. You make one complete circle like this. You start from here and you make one complete circle like this, and you end at where? You end at same point. It looks as same point. The value of z is now r e to the power 2 pi I, but it is not recommended to put e to the power 2 pi I equals 1, because if you take the whole power as 1 by 2, this according to this function z to the power half, the resulting value of this is square root of r and e to the power pi I, and e to the power pi I is not equal to 1. Okay, so this is why here the students make very common mistake. Here you can put e to the power 2 pi I as 1, right? Here you can also put e to the power 2 pi I as 1, but for this expression you cannot replace this e to the power 2 pi I as 1. This will lose the beauty of this. Now let us move forward to this third integral. For this third integral EFGH, the value of alpha is small r e to the I theta. So everything will be same like this. The only difference will be, and yes, so in this case I have already told you that theta varies from 2 pi to 0, not from 0 to 2 pi. This time it varies from 2 pi to 0. So now the limit of theta will be 2 pi to 0. And this capital R will be replaced by small r. So r e to the I theta to the z minus 1 divided by 1 plus r e to the I theta, and this is r I e to the I theta d theta, right? R I, yes. Now what about this fourth one? So the equation of HA, I have told you that the equation of HA is alpha equals y e to the power 0I. Okay, so if you put it here, what is the limit of y in this second part, this second integral? It is from capital R to small r, yes. And in this fourth part, the limit of y is going to be small r to capital R. This all has been told earlier in this video. So now it is y e to the power 0I to the whole z minus 1, right? 1 plus y e to the 0I, and this again e to the 0I dy, right? The sum of these four parts, the sum of these four parts, this whole, the sum of these four parts is equal to this value. So this is the RHS and this whole is the LHS, right? So now I wish to find the values of these integrals separately, and also, as I have told you earlier, ultimately I will be taking limit. Yes, I will be taking limit capital R tending to plus infinity and small r tending to 0, right? So I am going to do two things now. So here, let me move to the next slide. The first integral becomes, or let me tell you directly, let us again have a look at this. If you take limit capital R tend to infinity, okay, if you take limit capital R tend to infinity, what happens there? This is actually, let me clarify some things. So you are having r e to the I theta to the whole z minus 1 multiplied by r again and divided by 1 plus r e to the I. You are having this, and you are looking forward to take limit capital R tends to plus infinity, right? Okay. And one more thing there is that real part of z lies between 0 and 1. So now I'm again going to use this condition, right? Real part of z lies between 0 and from this you will also get to know what is the importance of this inequality here. So since just separate this out, e to the power I theta, I am only interested to the terms involving r, right? So I am having r to the z minus 1 right? R to the z minus 1, and then again multiplied with r. So what you can do, you can write it r to the z actually. You can write it r to the z and divided by r to the z divided by 1 plus r e to the I theta, right? Okay. Since real part of z is less than 1, okay, so the value of z will be something like, for example, let us take z as, and it is 0 greater than 0 also. So for example, let us take z as 0.9 plus I times anything, I times 10, okay. So this is 0.9 plus I something multiplied by something like 10, okay. So if you just put the value of z here, and you separate out real part and imaginary part, and what will you get? You will get r to the z as r to the 0.9 and multiplied by r to the I10, okay. Now if you take limit r tends to infinity, since this power of r is 0.9 and that real part of z was less than 1, so this power is 0.9 and you are taking limit r tend to infinity. If the degree is less than 1 and you are taking r tend to infinity, so this will tend to 0, and this will be something like cos of something or plus I sine of something. So this will not make much difference there, right? So ultimately this will tend to 0. Why this will tend to 0? This will tend to 0 because of real part of z is less than 1. So we have used this part, real part of z less than 1 here, okay. Now let us think about the other thing, other circular integral, that was limit r tend to 0 and it was small r to the power z minus 1. I have separated out these e to the power I theta like terms. I am only interested in this term r here, r 1 plus r e to the I theta, okay. Now I will use this real part of z greater than 0. So this is limit small r tend to 0 plus here, and this is r to the z 1 plus r e to the I theta. Since r tends to 0 and this z real part of z is greater than 0, so again let us put same thing, z equals 0.9 plus I into 10 or I into anything, imaginary part can be anything, but suppose the real part is 0.9, okay. So you will get r to the power 0.9, right? And you are taking this is not negative power. What I mean to say there is you are not going to have negative real part here, so you are not going to have negative power of r, right, as a real part. So r will not jump to the denominator. R will keep itself in the numerator, and if you take limit r tend to 0, you are going to have 0. So I have used real part of z less than 1 also and real part of z greater than 0. Using these few important small things, this term will vanish, and this term will also vanish, right? So what are the terms you remain with? You remain with only y to the z minus 1 into e to the power 2 pi I z minus 1 upon this e to the power 2 pi I, you can put 1 equal to 1. So, and the limit is capital R to small r. Capital R tends to plus infinity and small r tends to 0, right? So you get infinity to 0 y to the z minus 1 divided by 1 plus y, and that e to the power 2 pi I is 1, and yes, e to the 2 pi I e to the power 2 pi I to the z minus 1 it was, I think. Yes, z minus 1. So e to the power 2 pi I to the z minus 1 into dy, right? And the fourth integral, that was line 0 to infinity, and here you will have y to the z minus 1 divided by 1 plus y, and yes, it will be e to the 0 I, and e to the 0i is directly 1. There's no difference if you divide 0 by anything like 0 by 2, 0 by 3. Whereas if you divide here 2 pi I by 2, so it will become it will give you a new value. If it is divided by 2, you will get e to the power 2 pi I, and it is equal to -1, right? But here if you divide 0 by something, so it is not going to make any difference. So what you can do here, you can directly put e to the power 0 I as 1, and to the whole power is z minus 1. So this is 1 to the power z minus 1, which is directly 1, but this is not equal to 1 directly. I have already discussed it in this video, and this will be equal to 2 pi I, that was 2 pi I, and it was e to the pi I z minus 1, right? Now what we can do here, we can, yes, we can do it something like, suppose, okay, we do it 0 to infinity, we get a minus sign, right? We get a minus sign, and this integral is with respect to y, so you can take this term out. Yes, one more thing, this is e to the 2 pi I whole z, and if you just remove this minus 1, you can just divide it by 2 pi e to the 2 pi I, and e to the 2 pi I is 1 here, so you can take common. What is common here? The term common is to this y to the z minus 1 upon 1 plus y dy. The term which is common here is with a minus sign, e to the 2 pi I z. Is it clear? Yes. And here you have same thing, 0 to infinity y to the z minus 1, 1 plus y, and nothing common, so you have just plus 1. And this is all equal to this. Okay. Now you get 0 to infinity y to the, sorry, yes, y to the z minus 1 divided by 1 plus y dy. It is equal to 2 pi I, and this is e to the pi I z, and this minus 1 becomes 1 upon e to the pi I, and e to the pi I is minus 1, right? So you will get a minus sign, okay, minus sign, and this whole is divided by this 1 minus e to the 2 pi I z, right? What you do now, you just take this minus sign here and divide by e to the pi I z, okay, in both numerator and denominator. What you will get? You will get, this will become plus sign, okay, so you have divided by e to the pi I z, so what remains? E to the power pi I z minus e to the power minus pi I z, right? And what you do now, you just divide this by 2i. You take this 2i, you separate this 2i and just divide by 2i here. So you can take this here, and what remains? Multiplied by pi. So what you get? Pi divided by e to the power pi I z minus e to the power minus pi I z upon 2i. What is it? It is sine pi z. Okay, so this was the result that we were trying to prove today in this lecture. So one more thing, keep in mind that about the homework that I have already given to you, that is about Legendre's polynomial. Okay, so keep your work ready. Okay, thank you.